All right, welcome everyone. This should be the first video in chapter 7, and to start off, I want to do it fairly generally, and we should start off with talking about what a physicist means by work, okay, or what a physicist's definition of work is. And so I think it's best to draw a picture. So let's start off with some semi-horizontal surface, some flat surface, right? And then let's put an object on there. So I'm going to make that some box, all right? So if I ask you, which direction should you apply a force on this box to move it across the floor most easily, right? Which direction should you push or pull in order to move it, right? Most efficiently or most easily. Just from your everyday life experiences, you may think or you may say, oh, let's do it that way, right? Let's apply a force like that such that it moves in that direction, right? And you would be correct. Your intuition should also say if you apply a force straight down on top, it's not going to move horizontally across, right? But why is that, right? Mathematically, why is that? Well, knowing what you know about vectors, you should know that because there's no component of the force, right? If you apply a force straight down, there's no horizontal component of that force in the direction left or right. So if there's no force at all, it's not going to move, right? And you would be right. So by work, physicists really mean that's a relationship between a force, whatever it is, and an object's direction of motion, right? It's the relationship between force and the object's direction of motion. And so we want to come up with a way to write that as a general statement, right? For all forces and all directions of motion in general, right? Any combination thereof. So let's take a look. Let's say let's apply that force straight down, and I'm going to start it on the object and go down like that. So if we apply a force downwards, it's not going to move left or right. So in other words, the displacement would be 0. However, let's apply a force down at some angle, like that, right? That's another force. Now it does have a component. So, well, that was a big eraser. So now it has a component down, which we can draw as Fy, and it also has a component, we'll say in the x direction, Fx, assuming I have a coordinate axes, making there, x, making y down, right? And so this force will do some amount of work. How much work, right? Which component will move the object? The x component. The x component will move the object in the displacement direction, that direction, right? Displacement vector d. Okay, the y component here is again perpendicular to the displacement, so it's not going to move it. So the most efficient force is a force purely in that direction, purely in the x direction in this case. And so let me try and draw that here. So if I take away the old vector, like such, and now I apply a force purely in the same direction as the displacement, well, that would be the easiest to move. So to generalize, we have, let's say that's the third force we drew. We have this one that we talked about earlier, and we also have a force that's completely downwards. We'll call that F1, right? So a way to relate all of these together is you can dot them together. And physicists call this the work. It's a way to relate the force applied to the displacement, right, or how far it moved. The magnitude of a dot product, you may recall, is the magnitude of the first vector, so f, times the magnitude of the second times cosine of the angle in between. And so in the case of our drawing, the angle in between is right there, right? That's theta. And that can range from 0 to actually 180, right? I've only drawn it 90 degrees. Let's draw F4 to be 180. Okay, so what's the work done by force 1 here, right? The work done by force 1, say work 1. Well, it's written F1 dotted with the displacement, if any at all. Well, there wouldn't be a displacement, so work is 0. But we also know there's no displacement because what's cosine of this angle? What's cosine of the angle in between F1 and D? Well, it's 90. Cosine of 90 is 0. So either way, that force does no work. In the example of force 2, well, that does some amount of work, right? So that can just be F2D cosine theta, assuming you know the values. 3, well, that's just the magnitude F3 times D, and then the angle in between those is 0. Cosine of 0 is 1. So this work right here is maximum. Force 3 would do the maximum amount of work. And hopefully that makes sense because, well, if you apply a force purely in the direction that you want to move it, it's going to be the easiest to move. Okay? And that means that you're doing the maximum amount of work. And force 4, how much work does force 4 do? Well, it's the magnitude of that force, whatever it is, times the displacement. This brings up an interesting point. In one of my later examples, we'll calculate the work done by a force, but the displacement is in the other direction, right? So this would actually do a negative work because the angle in between F4 and the displacement is -1. So this would do the minimum amount of work. Right? Forces parallel to a displacement does the maximum work. Forces anti-parallel to a displacement does the minimum work. So what does this mean qualitatively? Well, in later videos, in one of my later videos, I will relate work with an object's change in kinetic energy. Okay? So if you apply a force in the same direction that an object moves, you're changing its energy the most. And if the inverse is true, if you apply a force in the opposite direction that it moves, you're decreasing its energy the most, right? So work is kind of a way to relate the force applied on an object to whichever displacement it has, okay? In later videos, we'll have examples of various forces on an object, but only one displacement vector, okay? So with that, thanks for watching.